time for us to do some problems involving Taylor polynomials. The basic idea is saying, hey, if all we use are derivatives and get tangent planes and we're great, what if we went and used second derivatives? Well, the answer is we'd be even greater in some respects. And so we're going to take a look, how do we find our Taylor polynomials and what are some things we can do? As always, as we're starting new topics, it's important to do some practice. The more we practice, the better we understand what's going on. So if you're following along with the video, make use of the pause button. See a problem that looks interesting? Pause it. Try it yourself first, and then see what happens. Well, let's begin. All right, our first problem. Find the second order Taylor polynomial for this function. Log of xy plus 2x squared y plus e to the power 2x minus 3y plus 1 at the point 1, 1. Now, what do? Well, let's just remember what the second order Taylor polynomial looks like. So, we have to specify a point. So this 1, 1, this is acting as our point A, B. So the second Taylor order polynomial will be the function at the point h of AB plus the derivative with respect to x at AB times x minus a plus derivative with respect to y at AB times y minus b. So in other words, the function, you can think of it as the zeroth derivative. Then we have the first derivative. So far, feeling very tangent plane-y. The second order says, hey, more derivatives. So plus hxx, second derivative, at AB, x minus a squared, divide by 2, plus, and the reason we need to divide by 2 is when we take the derivative twice, we bring a 2 down, and then we bring 1 down. So we need to have that over 2 to compensate for the 2 that comes down later on. All right, hxy. Now, I say later on, we're actually not going to take derivatives, but if we were, we would need it. All right, hxy, x minus a, y minus b. You can actually see what we're having here, right? Because it says, oh, we're taking one derivative with respect to x, one derivative with respect to y. We need an x term and a y term. Here we said, oh, xx, I need 2 x terms. So when you think about hyy, well, no surprise, it's going to be 2 y terms and divide by 2 for the same reason. So that if we got to the point where we did take 2 derivatives with respect to y, we'd have that 2 to compensate for the 2 that would come down. So in some sense, finding the second order Taylor polynomial reduces to finding these values of the derivatives, plugging them in, and then you're done. So mostly it's about knowing the form and then taking the derivatives and finally evaluating. Put it all together and you're finished. So there's not a lot to it. It's just a matter of, are you patient? Well, it's good to learn to be patient. So let's begin. Now, one thing we can do to make our life a little bit nicer is to say, if we wanted to, log of xy is the same as natural log of x plus natural log of y. So we could pull it apart. And so if we did that, it's just a little bit easier to keep track of what's happening. Okay, so I'm going to take a look at our various derivatives. We have h sub x. All right, so taking derivative with respect to x, 1 over x plus 4xy. And here, a 2 comes down, plus 2 e to the 2x minus 3y plus 1. Hy, okay, there'll be a 1 over y, 2x squared. And now, we say negative 3 comes down. When we say negative 3 comes down, what we're really doing is we're doing the chain rule, right? It's the derivative of e to something. So the derivative of e to something is e to that something times the derivative of the something, you know. In our case, it'll be negative 3 coming down, so minus 3 e to the 2x minus 3y plus 1. Now into our second derivatives, hxx. Derivative of 1 over x minus 1 over x squared. Derivative of 4xy is 4y. Remember, we're taking derivative with respect to x. And now, here, 2 comes down again. Plus 4 e to the 2x minus 3y plus 1. hxy. Well, you can take the derivative with respect to y for hx, or take the derivative with respect to x of hy. You'll get the same answer either way. So, taking derivative with respect to y of hx, well, there's no y in the first term. Derivative with respect to y here would get us 4x. So, 4x. And here, when we take derivative with respect to y, minus 3 comes down. So, minus 6 e to the 2x minus 3y plus 1. And hyy. Okay, so come to hy, take derivative with respect to y. Minus 1 over y squared. There's no y there. That goes away. And minus 3 comes down again. So plus 9 e to the 2x minus 3y plus 1. All right, there we go. That's our function. Or rather, excuse me, that's our derivatives. So the next thing is evaluate. See, we're not going to take these pieces and plug them in because they would look terrible, and it definitely wouldn't be a Taylor polynomial because it wouldn't be polynomial. So after you've taken the derivatives, you have to evaluate before you start plugging things in. All right, so now we're just going to evaluate everything at 1, 1. Well, that's a really nice number to use for evaluations. Since this 2x minus 3y plus 1 is consistently showing up, let's just quickly figure that out. It'll be 2 minus 3 plus 1, which makes 0. And e to the 0 is 1. Okay, so that's going to, just keep that in mind. All these pieces on the end, this e to the power 2x minus 3y plus 1, at the point 1, 1, they all become 1. So, we have the following. Hx at 1, 1. Okay, that's 1 plus 4 plus 2, 7. Hy at 1, 1. 1 plus 2 minus 3, 0. It's okay to get zeros, no problem. Hxx minus 1 plus 4 plus 4, 7. All right, great. Hxy, 4 minus 6, negative 2. All right, and hyy, well, minus 1 plus 9, 8. Now, anything else? Yes, what are we missing? We need to know what happens for h at 1, 1. Okay, what is h of 1, 1? Well, log of 1 is 0, so you get 0 plus 2 plus 1, which makes it 3. So now we have these coefficients. So the last thing is actually to write down our answer. So we get the following. Our answer will be h of 1, 1, which is 3, plus hx at 1, 1, which is 7, times x minus 1, plus hy at 1, 1, which is 0, times y minus p. Well, we don't write that down because it's the 0. All right, great. Well, what's next? hxx at 1, 1 is 7, so there's an over 2 there. So we can write this as 7 halves x minus 1 squared. hxy, x minus a, y minus b, that would be minus 2 x minus 1, y minus 1. And then hyy, at 1, 1 is 8, divided by 2, would make it a 4, y minus 1 squared. And we're done. That's it. That's the second order Taylor polynomial. So the process is actually not so bad. The big thing is to know the form. And maybe the hardest part is remembering the 2's. But with a little bit of practice, it becomes almost second nature. All right, good. Well, since we need a little bit more practice, let's do another problem, a similar one. Find the second order Taylor polynomial for the function x squared e to the y at 1, 0. All right, great. So we kind of have the process, right? So we're going to find our partial derivatives, evaluate our partial derivatives, and then plug everything in. So let's start by talking about our partial derivatives. So we have our function. We'll just write them underneath. F sub x, well, that would be 2x e to the y. F sub y, well, that would be x squared e to the y. F xx, so come to the derivative with respect to x, take the derivative with respect to x again. 2 e to the y. Fxy, so you can take the derivative of fx with respect to y or fy with respect to x. Either way, you'll get the same thing. 2x e to the y. And fyy at xy, well, come and take the derivative of e to the y the second time with respect to y, and we're still going to be at x squared e to the y. So now we need to do some evaluations. So in particular, f at 1, 0, well, that's 1 times e to the 0, 1. Fx at 1, 0, 2 times 1 times e to the 0, 2. Fy at 1, 0, 1 times e to the 0, 1. And so forth and so on. So you're going to feel like, okay, we plug things into e to the 0, 2. And you might say, wow, there's a lot of writing here. But you have to be patient. You never know. You got to do the work. And just see what comes out. All right. So we have fxx at 1, 0 is 2, fxy at 1, 0 is 2, and fyy at 1, 0 is 1. All right. Good. Whew. All right. Now, where to from here? Well, if we proceed, we actually just have to write down the answer. Now, if you remember the form, it's actually pretty quick. So what's the form? We'll write it again for practice so that we remember f of ab plus the derivative with respect to x at ab, x minus a, plus the derivative with respect to y at ab times y minus b, plus fxx at ab times x minus a squared over 2, plus fxy at ab times x minus a, y minus b, plus fyy at ab times y minus b squared over 2. Thank goodness we have that wide screen, right? Plenty of space to write it all out. But now we just go through term by term and plug in what we have. So we're going to get 1 plus, all right, 2 times x minus a plus 1 times, a is 1, so x minus 1. Okay, plus here we're going to get 1 times y minus 0 plus fxx is 2 times x minus 1 squared over 2 plus fxy is 2 x minus 1 y, and fyy is 1 times y squared over 2. Or if we just compress. Now, on a side note, I don't recommend multiplying things out. You could. I don't recommend it. So, what do we have? We have 1 plus 2 times x minus 1 plus y plus x minus 1 squared plus 2 times x minus 1 times y plus a half y squared. And there we go. Done. All right. Well, there's here's a little side note here. And I think this one is simple enough that we could actually pause and say, if you're a big fan of Taylor series, because who isn't a big fan of Taylor series? You know, like you're like, Taylor polynomials, they were my jam back when I took Calc 2. You might wonder, could we use something? And well, the answer is yes. And I just want to point out a little side thing. So, what could we have done? There's an alternative way to do this. And the alternative way is to say, x squared, and by the way, if the following things I say make you feel very uncomfortable, you're like, then you can feel free to ignore everything that I'm about to say. But I can think of this x squared e to the y. I'm going to write x squared as a Taylor polynomial centered at 1. Now, the thing is, you might say, isn't x squared already its own Taylor polynomial? And the answer is, it is a polynomial. And if you were to expand it, it would be the right polynomial, but it's not centered at 1. And forgive me, I'm just going to write this down. Please believe me, I'm not going to lie to you. So x squared, what's another way to write x squared? Well, you can write it as x minus 1 squared. That would definitely give you your x squared term. But now you have a minus 2x. Like, oops, let me fix that. So to fix that minus 2x, I'm going to add 2 times x minus 1. See, then now your x terms cancel. But now you're like, well, that's not good, Steve, because what do you have? We have a plus 1, minus 2. So if you add one more, then that's good. Okay, so this is x squared, but it's written as x squared centered at x equals 1. All right. Okay. We can believe that. Now, what about e to the y? Now, this is where we really are like, do you remember what happened with Taylor's series? E to the y is 1 plus y plus a half y squared plus dot, 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 dot. Now, the reason I go dot, 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 well, because there's definitely many more terms, but we don't really care about any of them because they're all high-powered. We care about low-powered terms. We only care about getting terms where we end up with quadratic pieces. So here's what we'll do. We're going to multiply these together, but only keep things where the powers would be at most 2. So let's see, what could we do? Well, for instance, the 1 times the 1, okay, that would be 1. We could do this 1 times 2 times x minus 1. Okay, that would be 2 times x minus 1. Or we could do this 1 here with the y. Okay, that would be plus y. All right. What else could we do? Well, we could do this x minus 1 squared times that 1. Okay, so that would be x minus 1 squared. We could do this 2 times x minus 1 times that half times y squared. Well, 2 times a half would be 1. So that would give us a x minus 1. Whoops. I'm sorry. I went out over 2 times x minus 1 times y. So that would give us a 2 times x minus 1 times y. There we go. And the last thing we could do is do a 1 times the half y squared. So plus a half y squared. And then dot, 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 dot. There's other terms. But the other terms in the dot, 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 all are at least 3, degree 3. And if you look, you'll see 1, 2 times x minus 1, y, x minus 1 squared, 2 times x minus 1 times y, and a half y squared. They line up. Is it a coincidence? No. Of course they'll line up. And it shouldn't surprise us that they line up. Because what really is happening is the second order Taylor polynomial is saying, okay, every function looks like a polynomial. And when we're saying the second order Taylor polynomial, it's like, okay, just look at the part of that polynomial up through degree 2. Is the philosophy. That's the spirit of it. And so what we did is we said, well, e to the y looks like a polynomial, as does x squared. Just rewrite it so it's centered at centered at 1. And now it's like, okay, this is another way to think of the polynomial pieces multiplying together and expand it out. Like I said, if this last part feels like very like, ah, it's okay not to pay attention. All right, let's move on. On to other topics. Well, but also fun topics, right? We shouldn't do non-fun stuff. That's not what math is about. Okay. So, let g of xy equal 3 plus 2x minus y plus 2x squared plus xy minus 4y squared. So I have this polynomial. All right, great. If g of xy is the second order Taylor polynomial f of xy at 0, 0, find all derivatives up through the second order at 0, 0. So in other words, this polynomial is the second order Taylor polynomial at 0, 0. So we're like, oh, this is great. This is perfect, right? So why? Well, what can we do? Well, we know how to write our Taylor polynomial centered at 0, 0. So what would it look like? It would look like f at 0, 0 plus fx at 0, 0 times x, fy at 0, 0 times y, fxx at 0, 0 times x squared over 2, fxy at 0, 0 times xy, and fyy at 0, 0 times y squared over 2. So I'm working on part A, centered at 0, 0. And now we say, well look at our polynomial. It's actually great. So we have 3 plus 2x minus y plus 2x squared plus xy minus 4y squared. And now we do our matching game. And we say, okay, well, our constant has to match with our constant. Our factor of x has to match with what goes in front of the x. So we start just listing our answers. This is the same kind of thing where I say, well, hey, you know, if I have the tangent plane, I can read off the coefficients and get partial derivatives. It's the same philosophy here. f0, 0 equals 3, fx at 0, 0 equals 2, fy at 0, 0 is minus 1, fxx at 0, 0, be careful here. When I divided it by 2, I got 2, so that would be 4. fxy at 0, 0, well, 1. And fyy at 0, 0, again, divided by 2, I got negative 4, negative 8. Great. Beautiful. All right. So this is the answer for part A. So I'm just going to make a note here. This is for part A. Now, part B says, oh, it's the second Taylor polynomial for the function, maybe a different function now, at 1, 1. So really, these two are not the same function. It's don't think of like, oh, here's part A, here's part B, and they're the same function. No. We really should change it. Let's change it. We're going to put this as an H, just so we don't confuse ourselves. Okay. So g of xy is second order Taylor polynomial. We also should put in words like of and for. Okay. Well, we'll fix that in post-production. All right. And so our question becomes, find all the derivatives up to the second order at 1, 1. We're like, okay, can we do the same thing? And the answer is no. Somebody has messed it up for us. And you're probably saying, what? How? Why? When did that happen? Okay, so how did they mess it up? Well, remember if you go back to the form of a Taylor polynomial, it's like x minus a and y minus b. So normally when we write a Taylor polynomial, it has things in that form. So if we were at 1, 1, it should have things like x minus 1 and y minus 1. We don't have that. It appears that someone took it and they expanded it all out because they were like, we're going to be really nice to you, so we're going to expand everything. And we're just sitting there, it's like, why are you doing that to us? don't expand, because sometimes when you expand, you actually make things a little bit harder to work with. All right, so now it's not a matter of reading off coefficients. So we have to adapt a different strategy. But there's a great strategy. And it comes down to an understanding. And so for part B, what's our new approach? Well, the idea is that Taylor polynomials work by matching derivatives. That's the whole philosophy. When we talk about Taylor polynomials, we're saying, hey, we want to find the polynomials where the derivatives match up as good as they can. So we're going to say for part B, sort of our aha, our derivatives need to match. Okay, now we could have done that also for part A, but because of the form, we could speed it up and just say, look, I can just grab it off the coefficients. So for part B, it's a lot faster to just say, well, let's take our derivatives. So we're going to take a lot of derivatives, and then we're going to do some work here. So gotta be patient. Well, that's all right. I think that's one of the things that we learn when we do Taylor polynomials. They gotta be patient because there's a lot of bookkeeping involved. The idea, though, the idea that says, hey, I can let things look like polynomials. What a beautiful idea. It's one of the most beautiful ideas that we have. So then g sub x will be 2 plus 4x plus y. G sub y will be, all right, let's see, we can minus 1 plus x minus 8y. G sub xx will be, come to g sub x, 4, g sub xy will be 1, and g sub yy will be minus 8. And now, here's the last part, part B. So for part B, we say the following. We say, look, our derivatives match, so h at 1, 1 equals g at 1, 1 equals, well, okay, 3 plus 2 minus 1 plus 2 plus 1 minus 4. Well, if you put that all together, for the plus part, 3, 2, 2, 1, that would get you up to 8. For the minus, it's 5. 8 minus 5 is 3. hx at 1, 1 is going to be gx at 1, 1. So you plug in 1. 2 plus 4 plus 1, 7. Okay. hy at 1, 1 equals our gy at 1, 1. Well, minus 1 plus 1 minus 8. Minus 8. And going to second derivatives, hxx at 1, 1 equals gxx at 1, 1, which is 4. hxy at 1, 1 equals gxy at 1, 1 equals 1. And hyy at 1, 1 equals gy, whoops, 1, 1 equals negative 8. And we're done. All right, good. Now, you probably say, hey, our second order terms were the same. 4, 1 minus 8, 4, 1 minus 8. Well, that's true, and that's actually not too surprising if you think about what's happening. Because what will happen is that the second order terms, because there's no higher order terms involved, then we're just going to be able to grab them by looking at the coefficient of the highest order terms. So that's why it's not too surprising that they match up. But you'll see the lower order terms don't always match up. 7 minus 8, they don't match up with 2 minus 1. So that's why you got to do the work. Do the work. Okay, good. Well, let's try another problem. So our next problem. Here we go. Let g of xy be a polynomial. 7 plus x plus 3y squared plus 4xy plus 6x cubed plus xy squared minus 5x squared y. And it's the third order. All right. Going all the way to number 3. Okay. Taylor polynomial to f of xy centered at 2, 1. Use this to determine all the second order derivatives for f of xy at 2, 1. So it's actually going to be a very similar philosophy to what we just talked about. It says, hey, if I have a third order Taylor polynomial, then I need to say something about I match all the way up through the third order derivatives. Now, someone again has foolishly, because it should have things like x minus 2s and y minus 1s, someone said, oh, for your benefit, we'll expand out. Oh, please don't do it for our benefit. It really isn't helping us. But, well, sometimes they don't know, and so they just do it anyways. But our same great aha, we say, look, derivatives have to match. So, since we know that the derivatives match, and we're saying we're after the second order derivatives, well, what we'll do is we'll start by looking at gx. All right, well, that's not so bad. That's 1 plus 4y plus 18x squared. Well, let me make that 18 a little bit easier to see as 18 plus y squared minus 10xy. And gy, 6y, and plus 4x. That goes away. Plus 2 times x times y, and minus 5x squared. Gxx, okay, goes away. Good. Derivative of 18x squared will be 36x. That goes away. And here, that'll be minus 10y. Gxy. Okay, that goes away. That'll be a 4. That goes away. That'll be a 2y. And here we'll have minus 10x. And gyy. All right, 6. That goes away. That'll be a 2x. And that goes away. All right. So there we go. Now, what's the key? The key is derivatives match. So we can say, we're only after the second order derivatives, fxx at 2, 1 is going to be this gxx at 2, 1, which is going to be, I'll put it in, 2 times 36 minus 10 times 1. So, okay, 72 minus 10, which is 62. fxy at 2, 1 equals gxy at 2, 1. All right, that's 4, and then plus 2 times 1, 2, minus 10 times 2, minus 20. 6 minus 20 would be negative 14. And fyy at 2, 1, well, that's going to be equal to gyy at 2, 1. Okay, so that's equal to 6 plus 2 times 2. So that's 6 plus 4 equals 10. And we're done. That's it. So this is just as reminding ourselves. And the big idea for Taylor polynomials, the big idea, the reason we keep emphasizing it, is that once you understand this philosophy, it's like, okay, I get it. I get what you're trying to tell me. That, lo and behold, as we look at Taylor polynomials, the derivatives match. That's what Taylor polynomials are trying to do, is we're trying to get all our derivatives to match up in a nice way. All right, good. Well, good. Let's try another problem. One more. One last problem to finish it up. And this one is a little different. A really small, different idea. Now, what does it say? Well, it says use the second order Taylor polynomial of this function at 0, 0 to approximate f of 0.1, 0.2. Now, what's going on here? When we talk about approximation, there's this nice idea of tangent planes. Tangent planes approximate the function at the point of tangency, because tangent planes kind of locally behave like the function. Well, so do Taylor polynomials. You see, Taylor polynomials are basically tangent planes plus plus. It's like we were adding a little bit more. So it's like, ooh, let's take that additional information and get even more value out of it. So, in essence, a Taylor polynomial is an even better approximation than just what a tangent plane by itself is, because it's using more information about the behavior of the function. So what do? We're going to find the second Taylor order polynomial, and then we're going to plug in the point. Okay, so actually it's not so crazy. We just have to work the process. And by now we've done it a couple times, so hopefully we're getting pretty good at the process. So we have our function, which is 3x e to the y plus 2y e to the x minus 4xy. So we work through all our derivatives. Derivative with respect to x, 3e to the y plus 2y e to the x minus 4y. Derivative with respect to y. All right, that'll be 3x e to the y plus 2 e to the x minus 4x. Derivative fxx. So the second derivative with respect to x. Go to the first derivative with respect to x, do the derivative with respect to x again. The first term goes away, and here we'll have 2y e to the x, and that term goes away. Okay, all right. fxy of xy. Well, what will that be? Well, take the derivative of f sub x with respect to y. We're going to get 3 e to the y plus 2 e to the x minus 4. And fyy, well, what are we going to get? Well, come to the derivative of f sub y, take the derivative of that with respect to y again. Well, we'll get 3x e to the y, and then these terms don't have y in them, so they go away. All right, good. So, next, evaluation. We've taken all our derivatives. Now we collect the data. What's happening at 0, 0? Oh, 0, 0 is a wonderful thing. Pretty much anything that's down below that there's a variable knocks the term out. E to the 0 is 1, so we're going to get 0, 0, 0. 0. 3, 0, 0. 3. Okay. 0, 2, 0. So that's 2. Here, that's 0. That knocks that term out. fxx at 0, 0 is 0. fxy, well, 3 plus 2 minus 4. Plus 1. Yeah, 5 minus 4 is plus 1. I know that one. And 0 times e to the y is 0. And that's, as I look at that, why did I drop my parentheses on that last one? Okay, we should put the parentheses back. X comma y equals. There we go. All right. Now I feel a little bit better. Things should be parallel. Should be consistent with our notation, right? Okay, so what's going on? Well, what we have is that our function near 0, 0 is very much like the Taylor polynomial. So f of xy is approximately, okay, so we're only going to keep the things where we see contributions. So let's see, where do we see contributions? Well, why did we say, I think one of these terms is wrong. That's not 0. That's, oh my gosh, I'm sorry about that. That's 2, isn't it? Right? Because it's 0, 2, 0. So 2. I was going too fast. All right. So notice there's only 3 terms that are non-zero. So, okay, so the derivative with respect to x is 3. And so that would be a 3x. Derivative with respect to y, 2y. And then this mixed derivative would be a 1 times xy. So plus xy. So that's what the function is behaving like. So this time I didn't write down, okay, all these derivatives times various combinations, because hopefully by now we've been practicing enough. Like, yeah, we can do that. No problem. No problem. All right. So we can say, all right, f of 0.1, 0.2 is approximately 3 times 0.1 plus 2 times 0.2 plus 0.1 times 0.2. Well, that's 0.3 plus 0.4 plus 0.02, or 0.72. Now, if you look at what's happened, in some sense, what you could say is the tangent plane would tell you 0.7. So only using derivatives up through the first order, say, hey, it's about 0.7. Essentially saying, second order says, we think you're actually better off at 0.72. Now, the reason I say we think, there's always a little bit of error. And unless you're really, really close, the error starts to compound. And you might say, 0.1, 0.2, that's very close to 0, 0. But from a calculus perspective, they're pretty far apart. So, but I think this is a reasonable approximation. All right, great. Well, good. So remember, the mantra for today, for Taylor polynomials, make sure that the derivatives match, and the more derivatives that match, the better the approximation. All right, well, thanks for coming. I always appreciate when you come and join me. I hope you come back and we can work together again. All right, bye.